I am Cesar Pernalete. I'm currently PhD fellow at the University of Ghent. Currently, I'm working together with Professor Kevin Van Kim and Professor Joris Wood from the Laboratory of Chemical Technology in Ghent. Today, I will talk a bit about PRIME. PRIME is a simulation software that's been developed in the University of Ghent during some decades. It's well, you will see later. It's a tool that's whose main service is for hydroprocessing, and currently we are looking at the opportunities that are in bringing this software as a K-open tool. That's why the name of the presentation is challenges and the opportunities, because even though in the moment it's a plan, we've been already identifying some different potential ways about where to go in order to bring this tool as a K-open software. To do some discounts. Okay. It's here. Yeah. Okay. Well, there's a little delay, but okay. In principle, we'll talk about hydroconversion, which is this process that's modeled using PRIME. Hydroconversion is a process that brings vacuum gas oil, which is a heavy fraction that you can find in crude oil. It's a catalytic conversion, and the purpose is to produce light products such as naphtha, jet fuel, diesel, or lube oils. There's a more modern trend on which the hydroconversion, the products are used, or the intention is to maximize the light products to be also fed to steam cracker in order to produce building blocks for plastics. The relevant idea here is that well, it's a hydroconversion process on which there is a hydrogen supply, and it's a process that's typically performed in two stages. There's a first stage of hydrotreating using a catalyst of nickel molybdenum over aluminum. The main purpose of this stage is to remove contaminants that can be present in the mixture, such as sulfur, nitrogen. And there is a second stage, which is the hydrocracking. It's typically known as hydrocracking, which with a catalyst with a double function, an acid function and a hydrogenation function. And it's here where the hydrocracking reactions are taking place, where there is a transformation of the molecular structure of the mixture. And it is here where it's possible to bring from a mixture of 1,000 heavy molecules to a mixture, again, of 1,000 but lighter molecules. Since the vacuum gas oil is a very complex mixture, normally the detailed characterization of this mixture is not available. To be it possible to have approximations to the molecular composition, but via gas chromatography in 2 dimensions, for instance, but it's time-consuming and it's typically not available, especially in operational context. That's why the feedstock is typically defined in terms of bulk properties, defined in terms of specific gravity, simulated destination, and sometimes in terms of the proportion of the different compound classes. The products is also typically described in terms of these bulk properties. Well, having said that, PRIME, which is a software that I will talk about, PRIME stands for First Principle Process Concepts for the Evaluation of Complex Mixtures. Well, it's a tool, it's a software that's for evaluation hydroconversion processes. And more recently, the idea is to make a tool especially targeting circular processes. The idea is to go in line with the European concept of the circular economy, on which the amount of waste is minimized. In our cases, we're focused on plastic waste. The outline of this presentation is in principle. I will go a bit deeper on which the concept of from bulk properties to fundamental kinetics, on which PRIME is based. then Prime, which is the conceptual approach, and how it is offered now as Python framework. Some industrial applications of Prime, some examples about how it is applied in the context of a circular economy, and lately how we foresee the migration of Prime to be a capable compliant tool. As I was describing previously, normally the feedstock that process in the context of hydroconversion is described in terms of bulk properties. However, the kinetics on which Prime is based is a fundamental kinetics. It's a kinetics that consider detailed mechanism for the different reactions that takes place in the process. It's based on theoretical concepts of the transition state theory, with a judicious simplification with a methodology that was developed in the University of Ghent. That's a single-event MicroKinetic methodology, where the different reactions are grouped in types of reactions, in classes of reactions. Well, the point is that to be able to jump from bulk properties to fundamental kinetics is necessary a molecular description of the composition, and that's why we perform molecular reconstruction. And that this is a key aspect, because one of the main issues that or let's say challenges that are involved in the migration of the tool as it is to be offered as a open compliant package with all the functionalities available root here in the molecular reconstruction step. If there is availability of the molecular characterization of the mixture, well, the molecular reconstruction is not needed. But as I was explaining later, this is not typically the case in operational context, where normally bulk properties is the information that is available. Well, a bit about Prime. Prime implements for the commercial case a plug flow reactor that considers both phases, gas and liquids. It's a trickle bed reactor. Well, it takes into account diffusion in the assuming that the spherical shaped pellet, and the reactions are modeled following the single-event MicroKinetic methodology. Well, this is a brief overview of all the reactions that are taken into account in Prime. Well, the main reactions are methyl chip for hydrocracking, the hydrocarbon reactions, ECP branching, beta scission, and also for naphthenic compounds. Debranching, ring opening are among the main reactions. It's very important to notice that there's a huge amount of reactions that are considered in the stoichiometric matrix, and are in the order of thousands for some cases, as the case of beta scission or exocyclic beta scission. Some few thousands of reactions are taken into account. Well, conceptually, how Prime was developed. So this is normally a hydroconversion process that, as I was explaining, is a process of two stages. First for hydrotreating and a second for hydrocracking. And then Prime creates different classes of objects depending on the different objects are that comprises the flow sheet in that case. For instance, in the case of the stream is defined in terms of bulk properties. Then via molecular reconstruction, the detailed composition is determined. That could be that populate the variables in the inlet stream, that it's an object, and then different objects are created for the subsequent streams and reactors, and every reactor is linked to another object that are the catalyst. All this this software was written in an object-oriented approach using Python, but not all was written in Python. I will go into more details later. Conceptually, well, it's a combination of different objects that you can combine, following the logic of a flow sheeting environment. This is Well, a bit more detail about what's behind Prime. Well, it's a Python library that combines the different objects that I was describing before. Originally, Prime was developed with two separated software. One software for the reactor model that was written in C, another software for molecular reconstruction that was written in Fortran. But Prime combines the two softwares in order to make it much easier to perform different simulations of different scenarios and to combine them according to the flow sheet that's required to be modeled, according to the process configuration that's required to be modeled. Having two separated software, it's more complicated to evaluate different scenarios of reactors in parallel, of reactors in series, for instance. But now having a Python framework is more it's more easy to combine them and to manage them. Well, being a Python library, there are some first attempts in order to run the reactor model or in general Prime as a Cape open compliant model. It was via the Iron Python function of DWC that was written in the script, the Python script in Iron Python, and was used in Go Simulator, was successfully tested. However, the functionalities that can be reached this way are limited and do not include molecular reconstruction, as you will see. Well, these are some industrial applications for Prime. This is a case on which the simulation of real operational performance of a hydrocracking was modeled of some weeks of operations, and then the correspondence between the simulated and operational needs, it's very good. This is an example of one of the data points. These are the experimental distillation curve, and this is a simulated distillation curve. With Prime, it's possible to make a very good match of the simulated of the experimental data points in the via simulation, because it's possible to work with the molecular detail. It's possible to go from the molecular detail to the bulk property as well. Also, what Prime, one of the main goals lately, apart from the possibility to be used in classical configurations of a refinery of hydrocrackers processing vacuum gas oil, the idea is to make it also adequate to model more modern refinery configurations on which the fossil feedstock are minimized, and instead plastic pyrolysis oil can be maximized as feedstock for hydroprocessing. This plastic pyrolysis oil would come from thermal pyrolysis of plastic waste. That is the idea. And then the product, the target would be to tune the process in order to maximize the production of paraffins and isoparaffins that could be fed to steam cracking. This steam cracking is well known as process to be the building block the producer of the main building block for plastic production, which are ethylene and propylene. And then after the plastic life cycle is end, this plastic waste can be pyrolyzed, as I already said, and this way it's possible to close the cycle of plastics. There are some challenges that are involved in this concept, such as the different contaminants that could exist in the plastic pyrolysis oil, and also the difference in the molecular composition. For example, the amount of olefins that are present in the plastic pyrolysis oil is much bigger than the amount of olefins that can be found in fossil fractions. Indeed, in virgin fractions, there are no olefins present at all, but in some cracked heavy fractions coming from delayed copper, for instance, there could be some amount of olefins, but the amount of olefins that are present in the plastic pyrolysis oil that could range even to 50%, and with a lot of olefins that are very unstable. We've been working lately in adequate in Prime to be able to deal with these new challenges involved in circularity. We've been collecting data at lab scale. This is a Robinson Mahoney type reactor for continuous operation with a catalyst load of about between 2 and 20 grams. We've been performing experiments there of hydrotreating, hydrocracking of plastic pyrolysis oil, and there are some preliminary results that I will show you. There are some few data points here that we collected of hydrotreating, in this case, pyrolysis oil at different conditions, and in black are the simulation using Prime. We can see that it's possible to match the experimental data, and then, as in any other simulator, the idea is to have a wider view of the system without having the need to do more and more experiments. This is the feedstock of the pyrolysis oil that we were processing. In the x-axis, you see the carbon number. In the y-axis, the weight percent. In red, paraffins. In orange, monoparaffins, and in green, olefins. We see that an important amount of olefins are present in the feeds, and then this is how it's possible to see how the olefins are reduced by hydrotreating. This is a simulated case. Okay, now having said that, how we foresee the migration of Prime as a Cape Open tool. Well, in principle, it's a medium-term commercialization strategy. This is a software that in the moment that... Oh, sorry, that's it. That's great. Okay. Well, in the moment, it's a process that some test licenses are being delivered already, but in the medium term, Cape Open, so to bring this tool as a Cape Open tool is part of the medium-term commercialization strategy, and potential price require integration with foreign process flowsheet. I think this is typical case. However, specific features of the simulation approach that we make may motivate the consideration of different scenarios, especially the molecular reconstruction case. It's a scenario that needs to be thought carefully. As a case A, we could expose the reactor as a Cape Open unit operation. As I was telling previously, for few compounds, being one compound or a mixture of compounds, it's quite straightforward. I could use Iron Python and Coco, and it's possible to do it because it's just Python. It's possible to do it in a straightforward manner. The disadvantage is that for complex mixtures requires the detailed composition of the ingot, and that requires GC plus analysis, which is normally not available. The molecular reconstruction feature would not be available. It requires a suitable property package because the amount of compounds is in the order of some few hundreds. In this case, external thermo could or not be used in the model because internal thermodynamic calculations are made. Case B, it would be reactor as a Cape Open unit operation shipped without property package thermo units. In this case, that would bring more flexibility to use in different process modeling environments. The disadvantages requires for the support for thermo. Well, that's something that could be included as well. So this method here, that correspond to reactor where thermal included, should be will need to be exposed as a thermal property package thermal. And then the third scenario that we foresee, it's thanks of course Michelle, of course, for some discussions that we had in that regard, would be to expose Prime as a full process modeling environment. That would allow to include the molecular reconstruction strategy as part of the software, would give more flexibility for operational environment, of course, having the molecular reconstruction available as part of the tool. But that would require more development effort. That would be more a long-term goal. However, in this case, integration of molecular reconstruction in current process flow sheets would not be available even in that way. So that's the main limitation that we are seeing up to now, is how to expose the molecular reconstruction strategy in an standard way. That's where we see the more complicated challenge when offering these two as a open standard tool. Well, that brings me to the end of the presentation. Well, I would like to invite you, in any case, to share your thoughts in that regard. That's part of the idea of this, to share with you this our ideas. But as conclusions, Prime was software tool for multi-scale simulation of hydroconversion process using a fundamental kinetic engine. Well, it's one of the key feature. It allows to define feedstocks in terms of bulk properties and offer detailed composition of products as well, to do the jump between bulk properties and detailed composition. Well, it has an object-oriented software architecture, and it's currently a Python library. It's being successfully validated against pilots and industrial data for fossils and also for circular feedstocks. And the way we see to expose it as a open standard tool is as a unit or ship with the own thermal property package, or that would be in the medium term, and as a long term as a process modeling environment, if that's we decide that's a way to go. And that would be the only required option to include molecular reconstruction feature, but not being able to expose a molecular reconstruction filter as to be used in other software. Well, that's if you have some feedback, so I would really like to hear it.